technology, which is, I think, one of the most amazing things that come out of this place in the 20-some years I've been working here. So, without much further, I'd like to introduce Andrew Greene and Christopher Markieta talking about the art.
All right.
Okay, good morning. I'm Christopher Markieta, and I have recently joined the OSTEP team here at Seneca College this fall. I'm currently working on improving our network's infrastructure and backup system, as well as adding an IPMI system under OpenStack control, and helping Andrew Greene with testing Pydora on the Raspberry Pi.
All right. As our presenter, well, our introducer said, my name is Andrew. I work for CDOT. I've been working on releasing a customized version of Fedora for the Raspberry Pi called Pydora, and that's like my main duty right now. And okay, just on, I want to get a show of hands. How many people are familiar with ARM? Oh, okay. I wasn't expecting that. And how many people aren't? All right. So, oh, one person. Okay. So I just. Okay. So I decided to give this presentation basically just because when I explain to people I know like what it is I do at work, they don't really understand what an ARM device is or what it's used for, not understanding that they're basically in everything that we use today, small devices and such. So, start off by saying, what is an ARM processor? Does anyone know? No, can you give me a brief definition of what you think it is? Yeah, it is. Yeah, it's basically a advanced RISC machine, and what RISC machines are is they're reduced instruction set computers, right? And what does this mean exactly? Well, they're really designed for performance, right? And they perform a limited set of operations extremely quickly. So their main focus is speed and efficiency. ARM uses the RISC approach to processing. Sorry. Yeah. So moving on. All right. Some brief background in ARM is it was designed in Cambridge, the first ARM processor in the UK. Originally, these processors weren't familiar outside the UK because they were really used for educational purposes and stuff like that. But in 1987, the first commercial ARM processor was released. Does anybody know what that device was, or the computer that was released in 1987? Ah, correct. So, sorry, I got a picture here. All right.
It's kind of a computer like the old Apple or anything like that. The 1980s version of a computer for education or perhaps businesses.
Yeah, that's basically what it is. So in the early 90s, ARM separated from its parent company to form ARM Limited, which is the company we now know today for ARM, which is synonymous with ARM, actually. There's two basic approaches when it comes to creating a processor, which is the RISC approach and the CISC approach. ARM uses the RISC approach, which is, like I said, they focus on speed and doing things fast and efficiently, whereas CISC works on CISC stands for Complex Instructional Set Computing, right? Sorry, pardon me. Throat's just getting a little dry. So Intel, well, ARM uses like the RISC approach, like I said. Intel uses the CISC approach to develop their processors. And they're basically, they want to build the fastest and strongest chips for the industry. Yeah, well, I guess I kind of already spoke about this, but like I said, RISC is basically built for speed and efficiency. And CISC is more complex. It has more computational power, but they're generally less efficient. Some of the advantages to ARM devices are that they have smaller die sizes, and I'm not sure if you're familiar with what a die size actually is. It's just basically the technical term for the actual wafer that the chip goes onto. So, what? Yeah, chips. All right. So when you have a smaller die size, that basically makes the chip perform faster because the smaller the actual die size is, the better you get in performance. Right. Another advantage to ARM is, well, here's an example of a small die size that's used on the Raspberry Pi.
Which I'm sure many of you have already seen, at least here at Seneca, which is pretty small. It's about the size of a credit card.
Yeah.
So.
All right, so another advantage is development time. You can develop an ARM chip quicker than you could develop like Intel processor, basically. So one of the main advantages to doing this is that as the generation gaps, like as generations of devices come out, the power in this, like they basically scale up. They get better and better over time, faster because of these shorter development times. Also, chip size is another important aspect to developing a cost-effective processor. Basically here, the smaller your chip size, the higher the yield, right? And how this works is when you have a bigger processor, you have more chances of getting defects with like per chip, right? The smaller it is, the less the chance of there being defects during production. So this directly equates to like per cost. Like it makes chips cheaper to develop the smaller they are. Here's an example of the A5 processor that Apple uses in their iPad. There's tons of processors out there that are available, and we use them in our everyday devices. ARM sales pitch basically goes like this. It has the best MIPS to watts ratio, which is MIPS, if you don't know what that stands for, is million instructions per second, and they're generally used to measure how good a chip is, like how well it'll perform, like the value of that particular chip, right? So the better the ratio, the better the chip is. So this translates into more savings. So you get more bang for your buck with good MIPS to watts ratio. So manufacturers use this to measure the cost of actually, this is basically the cost of computing. So another important aspect of their sales pitch is that ARM processors are low powered. So in my opinion, this is their main selling point, is that who wants a device that's going to die every 2 seconds but can calculate a lot, right? Because you'd have to charge it every second or leave it plugged in. So they make a lot of money based on their low power consumption. So putting this all together with a small die size, shorter development times, smaller hardware, and low power consumption, it all equals to one cost-effective processor. So as you can see here, ARM's dominated the mobile market with processors leaving Intel in the dust because they barely produce any ARM chips at all. There's a few out there that they use. One way that ARM makes their money is by licensing the designs of these chips to specific companies like Samsung and Apple and various other companies. So they don't actually compete directly with the manufacturers. They make money based on like their licenses and royalties and stuff like that. So my next slide here shows basically where ARM's going in the future. They have the greatest market share is going to be basically in embedded applications such as credit cards, washing machines, automobiles, and they could sell a chip for anywhere between $1 to $2 per device, right? Which is very low. They can also compete with Intel's Intel processors, right? With their higher end chips that sell for about $25. Part of the reason ARM makes so much money is not in share sales, but sorry, not sales. They don't make as much money as Intel does per chip, but they sell a lot more processors than Intel does. So that's where they make most of their money. And Chris is gonna take over from here. He's gonna get a little bit more technical than I was with this, but there you go, Chris.
Okay, so ARM-based devices. A lot of devices these days use ARM processors. Can anyone here name a few? Yes. Right. Yeah, some of them do, yeah. Anyone else? Yes, of course. Yeah, so there are a bunch of different devices that are used with ARM-based processors, including smartphones, GPS navigators, even cameras, and tablets, of course. Next year, ARM will be releasing its newest line of processors, the Cortex-A57 and Cortex-A53. These will be based on the ARM v8 architecture, which will now consist of both 64-bit and 32-bit execution states. It will be the most energy-efficient 64-bit platform because it will be faster in terms of floating point operations and cryptography, and it will be faster than ARM v7, obviously. The Cortex-A57 will have a noticeable increase about 20 to 30% in terms of performance over the Cortex-A15. And it will use the same power consumption and will be 3 times faster than the leading edge system on a chip for the mobile market. The Cortex-A53 will, however, be in the same terms of performance as today's smartphones, but will only consume about a quarter of the energy. These new processors will be using 28 nanometer transistors and eventually shrink to 20 nanometers and then 14 nanometers in the future. As Andrew Greene mentioned before, shrinking the die size will help improve power efficiency and performance even more. A lot of companies have already started licensing this new generation of Cortex-A50 processors in the hopes to release their newest products with this new generation architecture in 2014. Okay, so these processors can be set up in a big little configuration, which allows for the maximum CPU performance as well as the most power efficient CPU, or anywhere in between depending on how much performance is required. The ARM's big little configuration combines the most powerful CPU and the most power efficient CPU. Big little processing allows for instant dynamic transitioning of the CPU based on the performance required. So this is a lot like your NVIDIA Optimus technology, where you can dynamically change your integrated graphics with your dedicated graphics depending on what your application wants. This will be really fast, so fast that it's seamless to the user, and could potentially reduce power consumption by as much as 70%. So ARM does not ARM does not build these chips, but rather designs them. So there are other companies like Samsung and Qualcomm who actually build these CPUs based off of ARM's designs, such as the Snapdragon and Exynos processors in today's smartphones and tablets. Telecommunications is one of the fastest growing industries in the world. Today, you can use your smartphone for creating content instead of using your desktop or laptop. You can simply capture, create, and edit your photos and videos directly from your smartphone or tablet. Now, writing documents might seem a bit tricky on a touchscreen for most people, but you can simply connect a keyboard or a mouse or even a large high-definition display to your ARM-based device, and it's pretty much a laptop or desktop replacement. Now, the iPhone 5S was the first 64-bit based smartphone, as many of you probably know that. But next year, in the next generation of smartphones coming out, there will be a ton more. So look forward to that. And the widespread popularity of these devices, ARM-based devices, have increased the need for developers to create cross-architecture support between x86 processors and ARM-based processors. ARM-based processors cannot necessarily run x86 applications natively, and even if it were possible, it's not going to happen anytime soon. x86 processors are more powerful, but they're not very efficient. So ARM-based processors are catching up in terms of performance, and they are more efficient, and they will catch up eventually. Sorry. These new processors do feature full hardware virtualization. So many of you know that hardware virtualization means you can access your system resources simultaneously. In terms of servers, this means you can actively run multiple operating systems on a single machine. But besides servers, this is also relevant to other markets. Like, for instance, many automotive manufacturers use ARM-based engine control units in their vehicles. So this can be very useful because if a certain module in your car fails, the rest of the car is not going to break down on you. It's still going to run because the rest of your components are isolated and they're not going to be harmed. And your smartphones as well, because let's say, for instance, you have your typical apps like Facebook and Candy Crush, and you're also a business person. You don't want your enterprise applications to be exposed to those apps, and you don't want Facebook to have access to your private information.
We're going to pass out some ARM devices that we use here at CDOT, I guess, if you're interested in seeing them. So do we have any questions or anything you guys want clarification on? Yeah, you would have to return these. So that I handed out right there is a Calzado board. We got a few of them downstairs that we're using to build Pydora. I believe that's our fastest ARM device. This is the BeagleBone. Oh, you can just pass it backwards. Yeah. Sorry, there was more questions.
I know for sure that it will be fully compatible with the ARMv7 32-bit applications. I'm not so sure about ARMv6, but I'm sure the same applies there. I think it would depend on certain features. I know a lot of ARMv7, like the Cortex-A15 does have hardware virtualization, but if that was required in some other processors, maybe not. I don't know if the ARMv6 could handle that. Right. Sure. Right. So ARM makes a bunch of different CPUs, and their naming convention is sorry, they design them.
Yeah.
And they make their different line of Cortex, such as Cortex A9, Cortex A15, and now the Cortex A57 and 53, which is a bit confusing because in terms of performance,
yeah,
they're not very
always
scalable.
go like you'd think the higher number would be the faster chip.
Yeah.
It's not always the case.
But that's not it.
Yeah, necessarily. Yeah.
Right, and sometimes it means more energy efficiency in the long run. Yeah.
To what extent is this ARM really posing an existential threat to Intel? Like, do they have enough inertia from all the legacy apps that will run on ARM that are already so widespread and enterprise, Intel still have like a good enough penetration in the server market and ARM is there. Like, are they like panicking?
Well, Intel wouldn't say that they're panicking right now, but I think they have a pretty big competition on their hands right now. ARM is still like increasing in popularity even today. Intel-based servers, I mean, they're still around, and they're still the most popular on notebooks, desktops, and servers. But I think ARM is making their way up the ladder.
Yeah, I think for now it's because like the technology is fairly new. Until it's like tried, tested, and true. They're not really going to be worried right at the moment. But as the technology gets better, faster, more efficient, it's definitely going to be a competitor in the server market, in my opinion.
So you talked about the latest ARM, I forget what it, 2.8 microns or something. Does that mean they're tied to a particular foundry process? I guess I have the impression that you could take their cores or SoCs and make them an entry foundry, not just TSX or whatever, you know?
That's above my knowledge. I couldn't comment on that because I really don't know.
Okay, well let me explain what the question is about.
Yeah.
The idea is that ARM provides various levels of details to companies, but the most detailed is they give like the design of the chip.
Okay, I think I understand what you're saying.
Normally the chip is just a part of the chip,
Yeah.
and then the other companies put around it on the same chip a whole bunch of other stuff. That's why it's called system on chip.
Yeah, SoC.
A little part of it. And if you're forced to use one foundry to make chips, that limits how many places you can go. But I have this impression, I'm not in the hardware, but I have this impression that each foundry has their own recipes for manufacturing semiconductors, and then there's different scaling rules and all sorts of crazy things like that. So the more specific you are in the design, the less freedom you have to take it.
Yeah, but there's different there's a lot of different various like varieties of ARM processors, right? So that would most likely address what you're saying. I think, anyways. You had a question in the back, sir? Yeah.
Right.
Okay.
I have a question about the instruction set.
Yeah.
So with each iteration of the ARM process,
Mm-hmm.
the instruction set also get larger to support newer technologies and newer optimizations.
Well, that's the 64-bit versions of ARM that's coming out that Chris was talking about. It should be able.
Right.
It will actually use larger instructions, right?
So they're really just trying to bring in 64-bit now because they want people to start using it, and a lot of servers nowadays already use 64-bit applications. So this is sort of going to future-proof it for later on. Yes.
The big thing about 64, I would believe, is to make larger address space.
Yeah.
If you go and buy
Right.
ARM chips now, a system, they top out at about 2 gigs of RAM because more than that is stripping over itself in the address.
Right. In fact, that's probably the main reason, right? 64-bit, everyone knows, okay, if I have a 64-bit machine, I can now support more than 4 gigs of RAM. But most ARM-based devices, like smartphones, don't feature more than 2 gigs. I know the new Samsung Galaxy Note 3 is probably the largest. It has 3 gigs. So right now, it's not very important, but it will be in the next few years, I think. But aside from that, having the 64-bit support will give you a larger virtual memory address space. So for applications that need it, they can take advantage of it.
But the 64-bit doesn't even have higher, more instruction sets.
Okay, well then I was incorrect. I was saying that they use the address space is what I meant, though, but not instruction set.
Well, if you look at it, the architecture I don't know, but
Well, somebody had a question?
Kind of along this orbit, like it says RMB8, the
Yeah.
So what exactly is like that 5S use? Is that like Apple's own
That
RMB7 RMB8 or?
it's a Cortex A15, I believe. It's not the newest generation of ARM Cortex CPU, but it does have 64-bit support, so it's kind of on the lines of innovation, but it's not ARM's latest technology.
Any more questions? Clarifications? Yeah. You don't know. Well, that's one of our higher end ARM devices, right? And it supports, I believe, like you can actually put RAM on the board itself, right? Yeah.
Yeah, it goes into our
We're using
Veritas.
it. Well, okay. Good.
It's in our Veritas chassis in the armory down at CDOT. It's running in addition with 2 other cards that are basically our builders for building packages for Pydora. And yeah.
See, he's an infrastructure guy, so he deals with the hardware more than I deal with it.
I don't recall seeing any SD card readers, but
We do network install.
oh really?
Yeah.
Well, it's sorry, what?
It's basically what it is. The nodes, talk about the nodes.
Yeah, it's basically a giant server that can fit up to 12 of those cards. Each card has 4 of those SoCs on it, and you can
How many? Okay, how many of them are we using downstairs right now?
12 right now.
12. Okay, so and on each chip there's 4 nodes per chip, right?
Mm-hmm.
So how much nodes do we have altogether clustered?
No, we have 12.
Oh, 12 in
nodes,
total. Oh, so
3
we
cards.
have 4. Sorry, we have 3 cards that hold 4 nodes on it. So we have basically we cluster them together to create like one big network of machines.
And they're very low power. They only use about, if you had the whole Veritas server loaded up with these cards, 12 cards, and I think that's around 50 nodes, that only takes about 300 watts of power consumption. So, yeah.
So basically, it's a component of an ARM cluster.
Yes.
Yeah.
There was a question in the back. Oh, okay. Yeah. So. Sorry, I didn't. You got to start again. I didn't hear you. Sorry.
Does ARM provide open source version of their basically to like students or educational purposes if they want to design something for research?
That is a very good question. And I don't have the answer for you. I couldn't.
The actual core that you can get and the chip design of your own, that of course is not open source. That sounds really
They license that and yeah.
But if you want ARM programs, there are just a bajillion of the little toys of the Raspberry Pi. And as far as open source, there's lots of ARM open source. The whole picture is there because almost none of the news are disclosed. So you have to get proprietary blocks and most of it. There's some mostly open source, like the Raspberry Pi or the Eagle Bone Black.
The Raspberry Pi got broad on chip.
Yeah, everyone has a video blog in some form. It's unfortunate, but I think that's the state of the art, but other people would know better. Maybe Chris knows the actual state of the art better.
With respect to open specifications?
Yeah, is there any completely open software
of that? Are there any that are totally open regardless of why?
Not from ARM, but there are a number of licensees that combine ARM core with a non-ARM that is well known or documented.
Like what?
Well, the rest are quite a bad example, but that is a GPU that is a non-ARM that has been started with it. But obviously, NVIDIA is getting into the average, so there's some very simple ones, like older SIS chips and so forth that know how they work, and some vendors have those coupled with an ARM CPU and so forth.
Mr. Taggart, the biggest store, they were sort of, I read it, my understanding was they were kind of losing in the marketplace, so that they pull out this open sourcing the graphics side of it and as a way of saving themselves. Is that fair?
But across all platforms, whether it's x86 or ARM or any other platform, the CPU is always the sticking point. And the vendors, when you get to the candid moment, just the reason the vendors don't want to fully disclose their GPU specs is that everybody's stepping on everybody else's patents. And so they're just worried about a massive patent nightmare if they fully disclose.
But the fine point is there are, in the x86 world, there are open source reasonable drivers for the important ones. Really good drivers for Intel and pretty good drivers for API and good enough drivers for NVIDIA. So that's much better than using ARM as I am.
We're approaching that at ARM. We're getting basic to moderate open source drivers for a lot of this.
Really? Okay, that's interesting.
Okay. Anybody else? All right, then
Can I speak briefly about that quad core?
Sure.
Sure.
So one of the boards being handed around has 4 obvious large silver chips on it. That's like Calzeda, over there, right there. That's like Calzeda Energy Core card. Each of those nodes is a quad core system on a chip, so it's an entire system, and has 4 times 10 gigabit full duplex links. So each device has 80 gigabits of network I/O on it. So you can take those cards and you can stack them many cards in a chassis. Each card having 4 nodes, each node having 4 cores, all connected by this multiple 10 gigabit network fabric. That's a PCI layout connector, but it's not a PCI connector. It's a proprietary pinout on that. How much is it? So you're running $400, $800 a node, but this is early days, right? That'll come down substantially. What's really interesting is that's a dress rehearsal for what's coming next. So that's a Cortex A9 level 32-bit quad core. Next generation will be Cortex A15. Next generation after that, we're talking probably January 2015 timeframe, is full out 64-bit, and the network speed is going to jump up from tens of gigabits to something substantially higher. So we're looking at a situation where we have a quad core, maybe an octa core, 64-bit node, drawing 5 to 8 watts, and having probably hundreds of gigabits of connectivity. So that's what we're looking at for ARM hyperscale server systems. About a year out from now. It's going to be fun.
All right. So in conclusion, I guess, ARM efficiency is the way of the future. So that's really what ARM's all about. And this is our presentation. Thank you for coming out and enjoyed doing it.
On behalf of Seneca and FSOSS, I'd like to thank Richard and Christopher. It's tough when you walk into a presentation you're maybe introducing something to somebody and find out everybody already knows what you're talking about. So I think you did a great job. So thanks very much.
Thank you. Appreciate it.
I believe there's one more session before lunch.